In the PauliZtutorial module, you'll see for the first time the mathematics that define quantum mechanics. So this is a state vector. Normally, if you see a single sigil, it doesn't mean there is only really a single sigil. There is always a second sigil, just that it has zero information, right? So that's why you would have here 0 plus y or x plus 0, right? Because this is the natural state of quantum mechanics. To describe the state, you have to describe all possible states. Of course, to reduce the amount of paper, you just say that, well, I'm not going to write them down. I'll do their 0. That's a thing that I'm trying to showcase here through a lot of words that might be too much for some people. But again, if you look at the visuals, they are more than complete, which means you see this right here. This is the Z gate. This is the first time you're looking at a phase. This means that a 1 can now become a negative or a positive or a real or imaginary. And that's what the phases do. They introduce a complete plethora of possibilities on making your sigil be any number really, any number from the complex plane. So to just make things simple here, what we need to do when we have an X gate, the first thing that you need to keep in mind is that nothing will ever happen if your sigil is in the 0 state. So if your output by this row is in the 0 state, as is this case here, nothing happens. You can put as many Z gates you want. Absolutely nothing will change to your circuit. The circuit has to make sure that it flips the sigil into the 1 state. Yeah, which means it has to be on the 1, on that particular qubit where you place the gate. So again, the same situation, -1 multiplied by -1 will give you 1. So Z gates, just like X gates, are reversible. And then when we have 3 qubits, funny things start to happen. So now if I just add another Z gate here, what I get to see is that immediately this particular state becomes blue. Why? Because -1 with -1 will give you 1. And either case where a single qubit state is in 1, so either the rightmost or the leftmost is in 1, will have red. Otherwise, it's going to be blue for the case where everything is 0, 0, or it will be blue for the case where everything is 1, 1. So you can think on the vertical side and you can just count the number of lines and you will know if you need to place a gate or not. For the fourth part, it's again the same situation, but now with more qubits. So simply by adding another Z gate, we will immediately know that this will disappear, for instance, because only 2 of the states are in 1, which will give -1 -1 equal 1, right? And the same situation for either case in which only 2 of the bits are in the 1 state. So wherever everything is 0, or wherever everything is 1, 1, we'll get -1. Because again, -1 with -1 will give you 1, multiply with another -1. That's why we can get a red ball here by simply, again, you need to make sure you can flip it, and then you'll see it happen. And for the last case, we see that these gates also affect the actual descriptor of the row. So this means our tensor now is a 4x4 matrix, and it contains a multiplication between Z and X, which means, as you can see, these 2 are flipped and they're positive. And these are for the cases in which, well, the leftmost is in the 0 state. That's why we have a blue X here. And here, with the case where it's in the 1 state, because the Z gate will trigger, we will see that the X showcased here becomes red. But we cannot traverse it, right? Why we cannot traverse it? Because there's no way we can influence qubit 1 to be in the 1 state before this Z gate. So what we need to do is add another Z gate here. And again, so it will trigger, right? But it will trigger for 0, 1. So we also need to flip the leftmost qubit to make sure that now when it triggers, it also takes the directional path to reach 1, 1. That's all you need to know about the Z gate. Remember, 2 important things. First, nothing will ever happen if your qubit where the Z gate is on, so the column does not contain an X gate before it. Yes, so always make sure before it, never after it. Or you could do it in the way I have it here, because as you can see, before this Z gate, there was already an X gate present on qubit 2, and that's why it triggers. And add them together, and you get this pretty visual, because the state looks like this, which is different than what you see on the top. And as you can see, it leads to a state change to -1. It pushes the state all the way in the corner. Thank you.